Your lunches?
Yes.
Good. Welcome this afternoon, ladies and gentlemen. This is going to be, I don't know if you've been in the other sessions, this is going to be a joint session with Open Mind, talking about HyperMILL and our Max machining, innovations with conical barrel cutters, and our partner Fraisa, one of many cutter vendors making these, but in our mind the most developed in this area, and therefore a great partner, also local. And Matthew Tapp will talk in the second half of this and explain his portion of this. So let's move along since we got two topics in 1 hour. Here we are. That's easy. Okay, so we're going to talk primarily in this hour about finishing surfaces. Everybody has to finish surfaces, really important because you want to, that's what people will see. The typical process on most parts is going to be ball end mills, and it's easy, it's well understood in 3-axis or 5-axis, but it takes a long time, a lot of passes, a lot of small steps. In some cases, when you have simplified surfaces, you can use a flank milling to the side of the cutter against the side of the part. In certain shapes, that's perfect. In other shapes, you get deflections, vibrations, and poor surfaces. For bottom type surfaces, you can use flat cutters or fly cutters. Again, there may be limitations with undercut or long lengths. So finishing itself as a topic is becoming more important. Almost every CAM software is offering a high-performance roughing, whether from Celerative, which is our partner that we license with, but in the little pie chart we're trying to say if roughing is less time than it used to be, assuming it was half-half, now the finishing is a bigger issue, let's solve finishing. So we looked at this, watched people cutting parts, and looked at the time of finishing and tried to come up with a process. We looked at planar surfaces first. Planes would seem simple, they're easy to work with, but there's a lot of planar surfaces in the world. Large automotive molds, aerospace, structural parts. We looked at ruled surfaces, similar but slightly more complex, and then just generally arch surfaces. And you can see that out in the shop on the 520 machine later on. We'll talk about that here. So the concept we came up with, being a German-based company, was a barrel cutter. It's not a new type of cutter, but it's a new implementation for barrel cutters. And since we're machinists, small joke, we have cooling through on our barrel cutters. So these are barrel cutters styles that I purchased when I was working in a shop in the late 80s. It would take 8 weeks to get a cutter. The project maybe was done in 4 or 5 weeks, so we didn't really use a lot of these. They were available, but they weren't very practical. Here we have, looking like our beer barrel, above and below the equator, but a fairly small radius was possible at that time. And then it was more advanced. They put a ball end mill on the bottom, and the last one, fairly common today as well, where coming tangent to the shank of the cutter and using this barrel. And it's not a bad solution, but we're going to talk about and understand why we can do better. So, let's see, get my buttons right.
Yeah.
So we're going to look at the ball end mill on the top. Each one has 7 passes or 7 cuts, and you can see even using this tangent barrel type cutter, the surface finish on the bottom is going to be much smoother. If we're running maybe a 50 millimeter radius on the bottom and an 8 millimeter radius on the top, it's sort of natural. As we do this, we get less deflection than that flank milling because we have a single point contact, so that's nice. And we started thinking how to apply this more and more. And we look here at the tangent barrel, and what happens when you increase the radius of the contact, the barrel. As you increase the radius, you can take a bigger step down. That seems like an improvement. But with this constraint to be tangent to the shank, as you increase the radius, you get a smaller arc. The cutter stands up, you get an interference, the only way past this is to lengthen your cutter or reduce the radius. So you're not quite optimizing your situation. Still better than just using a ball end mill, but not the right solution. So we went a little further with some aspects of this are patented, which is nice, so we can talk about this pretty openly. We developed in our high performance functions we call max machining. We have a cone angle here, in this case 17.5 degrees, and a large radius. And with that large radius we can take, we had 30 and 60 on the previous slide. Now we're looking at 1,000 millimeter in harder metals, maybe a little bit smaller, just to improve the machinability. And here we look at the same kind of picture with a conical angle together with two different size radii. The posture of the cutter does not change. So the cone angle is what's controlling it. We can design these cutters. Matthew has them cataloged. He can make specials. If you have a small drafted wall, you just need to go tilt away from it. And as with all 5-axis machining, when you're tilted away, you get a short cutter. You can get your holder into the work channel, and you can save cutter costs, and you can increase your manufacturability with a short cutter. So I think we hit most of the high points there. In this technique in Open Minds world, we call it conical barrel cutter. Matthew will describe it as their trademarked arc cut, a segment of an arc on the radius, so all the same. Here's a video. Did we do this right? Good. And it's what you expect. Step down here, the ratio was 30 to 1, 7 to 0.4. The timers are actually accurate. The video we're playing games with, but mathematically, we're going to save over 90% of your finish time. On a typical part, depending on your industry, maybe the overall part time is coming down 30 or 40%. Ruffing's the same, maybe some ball end mill and some small features. But these aren't small changes, these are big changes. And we've had this 4 or 5 years. The message is getting out. It's getting easier to describe this. People have seen it on the web. And now we're in this position where people are interested and it's not novel anymore. You can try this. Easy to try. A simple time study type of chart. Contact radius went up from 3 in this case to 1,000. Surface finish, we want the same. So here the number of passes by the time you calculate it out is more than 10 to 1. That's your 90% savings. People worry about the cost of the cutter. It doesn't cost so much. Maybe it costs more per unit, but if we're going to take 90% less passes, it's going to last maybe 10 times as many parts. So what's the cost per part? Very low. The cutter, if we recall from the other slide, had a ball end on the bottom. So you have a dual purpose, you have a second life. Also, we can influence the contact point. So if you have a hard metal and you're going to wear out the cutter because you're cutting titanium, nickel alloy, if you have a different contact point, you can, in this case, increase the life another 3-fold or more. So the cost of the cutter is your first obstacle. It shouldn't really stop you in any way. This is a proven, at this point, 5-year proven process. It's smooth and it pays back. The other benefit here, the last point, as we move the contacts down, we're also getting closer to leaving less material remaining behind, cleaning up into that fillet as best we can. So, nice operation. Here's some applications. Now we have a bottom surface. This is an airfoil structural part, 14 inches, 6 inches tall. If I came to do the bottom of those flat planes with a bullnose cutter and it's 6 inches long, and I need a 6-inch cutter because otherwise I'm going to rub this adjacent vertical wall, we have a problem because a 6-inch long cutter is not going to cut really well. So now we have a 3-inch cutter. It's a plane. If it's a side plane or a bottom, it's the same. Here we're just going to tilt up a very large angle. We're cutting what looks like the bottom of the cutter, but it's that same conical cutter just flowered out to a much bigger angle. So we can apply this to bottom machining, including here is a slight undercut if your part has it. You can't do that with a flat bottom cutter unless it's some oversized with a small shank. So some good things are possible. Here's a typical automotive fascia mold. The red surfaces are initial candidates just by looking at planes. So, this, I can cut that from the side, but it might be too large. I can cut this at an angle, but maybe the holder's gonna hit here. So these red surfaces are our candidates for barrel cutting on this part. If we look at the next slide, now I don't only do planes, but I can do any large radius surface. We can do almost the entire part except for the product features on the mold with barrel cutters. And we have customers redesigning their parts to enable more and more, because if it works, why not use it more often? So the applications could be in any industry. We don't want to cut, in our internal meetings, we don't want the Rocky Mountains up and down, but we're doing the medical spine plate on the machine out here, aerospace, molds, turbo machinery, anything with fairly large open surfaces. On the programming side, probably better if you're interested, stop by, talk to us on our table. But in our tool database, we have a barrel cutter style, and there's many geometry versions. This is from Fraisa's catalog. These 3 radii map out to 3 radii in our tool entry. It's very simple. So it's easy to apply this. You can build up a database. You can bring in tool parameters, and everything's easy to work with. Unlike other new technologies, you're already cutting your materials. You use 5/8 shank cutters. There isn't too much that's different, but the amount that is different is powerful. We then learned to like this, get some feedback from the first few early customers, and we said, I don't know if you can see it so clearly, this is some aerospace kind of part, but it's all patched up the way that sometimes CAD data comes in. We're running these tool paths over the surface, and we have to follow the surface parameters. So we came up with our own CAD function to refit a surface within a tolerance, and here to control and improve the parameters of the surface. Initially, we couldn't use the barrel cutter as effectively here. We'd have to do this surface and separately that surface. Now we can do it all as one. So we're increasing the application set for barrel cutters. And this spine bone plate was an example of this. We resurfaced it within tenths. So it's technically it's good, and it's smooth, and it works out well. So the standard barrel cutters are good. They're better than ball-end mills. The conical barrel cutters, better yet. Easy to program. Just click a surface. We'll check the boundaries, and we'll make the tool paths for you. Here's another case where we use the reparameterization just to improve the orientation of the cutter. So the UV is controlling where the cutter is going to be oriented. So that one worked out nice. Here on a planar surface, but in the middle of a complex mold, you can see a little bit, some smooth rapid or smooth entry and retract. There's also a color change, so when we move into rapid to reconnect, we're trying to be efficient. So we're not just focused on making a tool path go on the screen or on the part. We're making an entire overall process that's going to work out of the box onto your machines. The large cutters, when you have an internal corner, you may need to add some bounding passes, because the big barrel can't get all the way in the cutter, but we control and you can use the ball end on the bottom So everything's perfectly aligned. It's the same cutter, the same touch off on the machine, and you can get really nice blends with all this stuff. So we started saying everybody has some high performance roughing. Very good. We added high performance finishing. What remains after is, on many parts, is a fillet surface. And now on those fillets, you might still be doing some little Z-level step down with a ball end mill, and it takes a long time. So we've added and expanded again in our most recent release of the software, handling fillets either with a ball end on the bottom or for larger fillets, the barrel. So we can do it in far fewer steps. And this process, is primarily stroking up and down, or possibly up is actually more stable in some cases. And then at the very bottom, which we can't see, a little Z-stepping to blend in as you would typically do. So again, trying to use these cutters and taking out the remnants remaining time. So then a few little touch-up points to finish my portion here. We're trying to make a good part. Many years ago, our focus was to make a good tool path. If you had a good tool path, you would presume you get a good part, but there's some realities that happen in life. You know, the machines aren't perfect, excuse me. The cutter lengths, the probe touch-offs, the machine heats up. There's all sorts of reasons going on. The cutter wears down, maybe the biggest one, and things don't blend well. So making the good tool path on the screen was great, but our goal in the end is to make a good part that, as was mentioned earlier today, you can sell it. It's a part that doesn't need finish. So we could try to analyze all the physics that go on here, how to make a machine that holds tolerance in 85 degrees or 65 between morning and afternoon. So we said, let's bypass all the physics. It's not that hard. And we added some technology we call blending. And we've automated this blending, so you're not having to do a lot of CAD work to modify surfaces. First kind of blending we're doing is just the way we overlap. Typical process is steep and shallow sections programmed and cut differently. With this small overlap and then a small lift, so you don't come in together, just with a small lift, one button in the software, and you can't find where that crease is anymore. Here, similar example, we're now in a fillet surface. So we cut this large wall, however, hopefully with barrel cutters. Then you come down to the fillet, and you have a small cutter. Maybe you've tilted it off to reach in there. And all of these issues about the physics on the machine come back into play. So I've exaggerated in this picture, but as we get to the top and the bottom of the fillet operation, we're going to blend out. A little bit of an overlap, and then a blend out, it's gone. So we initially released this to 2 alpha customers. One was making 6-foot steel blocks for these automotive fascias. First part off the machine, this is great. The inspector can come in from his automobile supplier. He's going to accept this. They would never accept the first one. The second customer was making small thermoform molds. You go to the supermarket and you buy blueberries and strawberries. Those baskets are made with HyperMILL. And he doesn't care about dimension, he just cares about the visual look, because in the end it's garbage. You eat the berries, you throw out the plastic. But he needed this blending. He had a 10-year-old machine, and he says, I know HyperMILL's not the problem. My machine isn't keeping up. Please help me. We offered him the solution. He's still running the same machine 2 years later. So again, we apologize for not helping the sales of new machines, but customers are looking for solutions that make sense in their daily business. Also in the latest version, and we're still collecting data, but a new fantastic operation, almost every CAM software is running surfaces to a mesh that sits on top of a surface. And this is a standard operation used in most CAM software. If you have multiple surfaces and blendings, It's hard to manage it in the cam by putting one consistent mesh over the surface. We can treat all surfaces the same. We cut the mesh. So now it's a little hard to see as always because we're talking about microns, but we cut to the mesh and then we push it down to the surface. So we're actually cutting to the actual surface. We've had comparisons done against 3 or 4 other software. This result is making the difference. Where people are seeing in one of these examples, in metric, we moved 0.002 millimeters, 2 microns, and that was enough to make the difference of a faceted look on a surface to a perfect look. So again, focusing on finishing with the barrel cutters, here just on surface finish quality itself. And we're doing, I think that's it. Matthew's going to continue. Talk about how the combination, software and cutters, and if you have questions, let us know or find us here.
Some of the modules is not barrel cutters.
And that barrel cutter's using to make that little cam part out there on the 5th axis.
We have 4 different ones actually.
Okay.
2 are similar shape. One's a 4 flute versus a 6 flute. The 6 flute, of course, being the higher finish.
Okay.
We actually I was able to extract a curve off the shape of the model and analyze the shape of the curve. And Fraisa was able to make me a custom form tool that catered to that specific application. So, and then there's a 4th barrel tool that's much smaller that I actually use for ice machine. When the rad is getting machined, it goes from the tip to the actual side of the barrel. The software is able to calculate that changeover between ball and barrel, which is quite nice as well. So I had some fun with it. I used the barrel cutter for some swarfing as well, just to kind of have some fun around the inside circles. Maybe the dimensions that aren't so critical, just having fun with it.
Yeah, they're good for our chemical.
Good. So what I'm going to talk about basically, basically is this R-Cut X, what we call our barrel cutters R-Cut X. The different styles of barrel cutters that we've produced. I'm going to talk about a little bit of the geometry behind them because it makes a big difference how you grind these tools, whether or not they're going to work on this software and in these applications. Then we're going to talk about where to use a little bit more. I'll expand on a couple spots where Alan already took us there. One use case that we have, we're going to then talk about our tool expert, which is really when you're programming with this software, how are we going to get the right speeds and feeds to use these barrel cutters? So that's not just a given, we have to be able to figure that out. So we actually produce spherical versions of our cut, so these barrel cutters, that's a barrel to ball. And then we produce a toric version. If you don't need the ball nose at the tip, then basically we have just a 3rd corner radius, so kind of a bull nose to barrel. And then we also produce this, what we call a floor finisher, could be a lens finisher, whatever it is. That's the steep angle version where we're going to be able to finish any flat horizontal surfaces. So we see here that the cone shape on our floor finisher here is above a 50-degree angle. We, as Fraisa, got lucky because we came into this a little bit late, so we didn't have to go through the evolution. So basically, we have the conical, which we made basically to the specifications that HyperMILL wanted, and then we have the floor finisher. So now we're hitting the steep areas with the conical barrel. The flat areas here, we're hitting with the same conical barrel, but more than 50-degree angle, so it's more of a floor finisher. And like I said, these tools were specifically designed with HyperMILL in mind. So the problem, again, as Alan showed with the tangential barrel, is the fact that we absolutely have to stick to a small radius, and so our solution, again, as well, was with the R-Cut, and with this R-Cut, we have variations of this 1,000 millimeter radius. So we're going to have a about a 15 degree, a 20 degree, a 30 degree version. So depending on what your working angle that you want to choose, you can choose the right tool to be able to maintain that working angle. So with the range that we've created, you should be able to hit the majority of the work that you want to do if you have the possibility of using a 250, 500, 1000 millimeter radius. But again, just like we did for this bone plate, if you have a radius that is smaller, then we can produce the right size radius like Peter mentioned. Take a look at what that concave feature is, and we can produce the right size barrel. It's still going to make a world of difference in time versus a ball nose cutter. So whenever Fraisa is producing tools for specific applications, we look at a variety of different things. We're not the only players here. There are some other high performance cutter manufacturers that are producing barrel cutters. But I like to highlight some of the things that Fraisa does. So we take a look at raw material, so what we're producing this tool out of, the carbide itself. And depending on the application, we choose different carbides for different types of features. So we're using, we call this our X10 carbide. It doesn't really matter. I can tell you I got it from the moon. It doesn't make a difference. What does make a difference is we tried different carbides in these applications. We tested the tools and we came up with what we thought was the best result. And when you're talking about a barrel cutter, it's just a giant ball nose tool. And so what we wanted was a very hard carbide that is going to withstand a range of materials, but also these light cuts and more heat than what we're used to in a roughing carbide, for example. So roughing, carbide that we use for roughing tools is more flexible. This is going to be a little bit more rigid. We've increased the core diameter. It sounds kind of, why wouldn't you be able to do that on, in any case? There's a lot more behind that. So this increased core diameter is a difficult thing to accomplish when you're grinding these tools, to keep it consistent. And also, I mean, I know Alan said that our tools, once you've used them in a 5-axis scenario, it's probably not very expensive, but we also, as Fraisa, always like to resharpen these tools. So you have to be able to make the tool and make it so that it can be resharpened. One of the key factors as well, H6 is the heat shrink tolerance. We grind ours to H5, so the shank tolerance is H5. That's going to mean better precision, better concentricity, more accuracy, less chance of, which you probably wouldn't in a tool like this, but having any slippage or pullout. Dimensional accuracy is also something that is very critical. So when we grind this tool, we look at an entire form, and on the ball part, it's every 5 degrees. On the barrel, it's switching again to every 5 degrees on that barrel. We are actually grinding that to plus or minus 5 microns. So our tolerance in that band is plus or minus 5 on the entire form. If we didn't do that, then we couldn't change from using the barrel over to the ball without having a blend problem. So grinding these tools to a very tight tolerance is extremely important. We offer tools with 4, 6, and 8 flutes. So the 4 flute tools are going to be for pre-finishing, or what we consider pre-finishing, and then you can switch over to a 6 or an 8 flute tool for finishing or super finishing. So now you're talking about even cutting your cycle time further down from there. We offer versions for steels and for aluminum. So depending on the steels or aluminum, we have either a coated version or special edge conditioning. So it's basically the same tool library that you're going to use no matter what type of material you're cutting. So again, for example, on this ball to barrel, we have a 30-degree working angle, 20, a 10, and a 6-degree working angle. And the 30 has the smallest radius of 750 millimeters. Otherwise, we have 1,000 after that. And each one of these has a ball on it, so a 4, 6, 8 millimeter ball. So depending on your fillet size, now we're going to select which size ball nose tool we want to be able to use the same barrel cutter as we do in those fillets. And with the floor finishing here, we really only have 2 sizes, a 65-degree angle and a 70-degree angle, and that's going to fit most of what you need. That gives you a working width of cut of 2 or 6 millimeters. So big step overs when it comes to finishing those floors. Here's an example of where we actually were able to get a part accuracy of 2 to 3 microns, and that is utilizing the barrel cutter part of the tool here, the ball cutter part in these corners and down in the fillet. So really, with HyperMILL and our tools and the way that they put that, utilizing our DXF contour into their software, you're able to match with no fillets at all. Or, sorry, you're able to match the fillets with no blending problems at all. So one of the big struggles that we had, or the big efforts that we put into, was how to utilize these tools, because we were pretty new in the game, so we had to work with HyperMILL, we had to program with HyperMILL, and we had to start test cutting. And so Fraisa over in Switzerland has currently 7 machine tools that we run tests on day in, day out. And here in Minneapolis, we have one 5-axis machine that we run tests on day in, day out as well. And so what we're trying to do is build application data so that our customers don't have to recreate the wheel. So we have these versions with the coating and a special edge preparation, and here's the range of materials that we are wanting to use there. So we tested these tools in all of these different material types, and then the version that has a polished flute with no coating, then we tested it in the very soft steels or aluminum, copper, and plastics. So we really have a versatile range of materials that we can cut with these barrels, and you don't have to put in new form data. It's basically the same tool that's going to do all of those different materials. So the application cases here, in steep areas, we have pre-finishing with the barrel that has a ball on it, so where we might have a floor, or we have pre-finishing on these walls that have no floor, and then we have finishing and super finishing. Now I can tell you, depending on the type of materials that you're cutting and what type of customers you have, most of the time, if it is an aerospace part, then pre-finishing is probably good enough. If not, then you can get into the finishing. So pre-finishing on a wall, you're going to be in the 5 to 7 millimeter step down range, something like that. In the finishing, you might be in the 1.5 millimeter up to that 4 to 5 millimeter range. When you get into super finishing, now we're really talking about no scallop height at all. It's very, very fine finishing. So we don't say that you have to program a pre-finish, a finish, and a super finish pass all the time. It just makes a difference on what type of parts that you're trying to produce and what type of precision you want on those parts. So same here with the radius area, so cutting with a fillet, that's now utilizing the ball. So the same tool. And then with the flat surfaces, we offer the pre-finishing, finishing, and super finishing parameters. So if we just look at a simple part here, which I guess it kind of looks simple, but it's really not, you'll see which areas we're utilizing the tools on. So in pre-finishing, in this tight corner here, we're utilizing the ball part of that barrel cutter, and then we take the barrel part of that tool and we finish the wall. So same tool doing both things, again with the floor finisher as well. So we're doing the pre-finishing and the finishing here. So with 2 tools, we're finishing this entire part. And we don't have extreme long stick outs. We have a very stable process. The tools last, like Alan said, a very long time because they're taking very few passes compared to if we were running a ball nose. So again, single surfaces, free-form surfaces, we're talking about double curvatures. If we're looking at very tight curvatures, now we can make special tools for that. So a real wide variety of parts that you can cut, and I have a few other examples that we did here. So a very small blisk that we produced with one of our micro barrel cutters. We're doing some bracket work here where you would ordinarily need a very long relief tool to walk down that bracket, so instead we're able to tilt this barrel cutter and cut that. This is a titanium box that had some features on the inside that you couldn't reach, a curvature on the floor. So a lot of complex parts, and realistically speaking, I think, and Alan could probably back me up on this, it takes a trained eye to take a look at a part and say where you can utilize these barrel cutters and really save time, and it's not everywhere. So I think between Fraisa and HyperMILL, we have a lot of customers that are either sending us prints or models and saying, what would you do? So that's, I think, a good solution. Send it our way, we'll take a look at it and say whether or not we think there's an advantage to it. If there's no advantage to using a barrel cutter, then certainly we're not going to tell you there is. So getting to the application part, we've created a software called Tool Expert for RCut X. And this Tool Expert, what it does is basically it looks at what you want to do for your application. So you can go step by step. First you choose your material type, so all of these different materials, tough to see here, but we've got mild steels, heat treated steels, cast iron, we've got stainless, both in a normal or a difficult, titanium, we've got different aluminums, coppers, plastics, tool steels, you name it, it's in there. So the first thing is find out what type of material you're machining. So here we picked stainless steel, for example, and now we see again we've got these choices of pre-finishing, finishing, or super finishing, and what type of tool we're going to use. Once we select the style that we're going to use here, we get into the size range. So I picked a barrel with a ball, and we've got the standard large sizes, or we have micro sizes that go down to a 1 millimeter ball. And from there, we can choose our working angle, and that's really the most important thing. What kind of working angle can we be at? What type of, how far tilted can our part allow us to be so that we can select our working angle? So here we chose a 20-degree working angle. We're going to do semi-finishing with a 4-flute version of that tool. We move on here. Now we've got our speeds and feeds for that tool. So depending on the type of work that you're doing, depending on if you're using the ball of the tool or the barrel, we have specific speeds and feeds for that, because it's going to make a big difference utilizing this tool on the ball for surface footage, chip load, so giving you RPM and feed rate, versus if we're using it up here on the barrel. So the application data is really right on line here, and this is going to give you a very good starting point, a good quality part, and from this data here, we just move on and give a PDF setup sheet. So now you can create that in the software right away. Now, if you have HyperMILL, I think we have a full catalog of all the Fraisa tools that we can dump in there. There are some other softwares. Alan doesn't like me talking about other softwares, but I bring them up anyways. But there are other softwares out there that are trying to make this happen. It's very difficult for them because they have because HyperMILL has a lot of patented technology in there. But we see the trend coming, and what that trend means to me is this is really a valid point. Whether or not they'll ever get to the point where they can do it as efficiently as OpenMind, I don't know. But definitely this is a valid point. So we offer this speed and feed so that you can plug that into currently into HyperMILL and get going. And all of the demos that we did on that 520 on the barrel cutters, except for the special barrel, because we had to come up with our own speeds and feeds on that one. But everything's just right out of this software. So it really is plug and play. You can tweak it a bit. You can maybe increase your surface or your feed rate if you don't need that good of a finish, or decrease it if you need a better finish. But for the most part, it's giving you very good starting parameters. So, and again, like I said, we like to resharpen our tools. So this is something that for us is extremely important. So we resharpen the tools back down to their plus or minus 10 micron tolerance on the big tools, 5 micron on the little tools. We make sure that when we produce the tool, we're making it so that it can't be resharpened. And then when we resharpen it, we want to make sure that it's going to work just like a new tool as well. So all of the features are going to be there. And then we use the same coating or edge preparation as we do on the new tools. So, and that lowers the cost of that tool at least by 30%. So again, it's not, don't let the cutter cost get in the way of you trying this, because it really is a very cost-effective way of getting this amount of work done. So again, if not everybody's been out there to see it, take a look at the MX520. That's where we're producing. This is actually either a bovine or an equine bone plates. So if your cow breaks a leg, then you might have to buy one of these things and put it in. But essentially what it's showing us is the possibility of processing on a smaller part as well. We didn't get very, very small, but we have done smaller bone plates than this with an extremely good result. And you'll see that it's a very high quality surface. You have to actually touch it. I don't know, are we just going to finishing out there?
The form tool, we went to finish. The general shape from the catalog, what you're seeing on the screen here, was the super finish.
Okay, okay.
Because of the form tool having such a smaller radius, which was 20 millimeters as opposed to what you're looking at here is 1,000, the step over gets of course much smaller, so it takes more time.
Sure. But if you take a look at it, you're going to see the step downs. You're going to see the tool path. You'll see that in every part that we've shown, but feel it. You really have to feel it. That makes a big difference. If you go out there and you actually feel the part, you'll notice that you might see the step down, but you can't feel the scallop. So, and like I said, in aerospace parts, it really, the pre-finishing, these bigger scallop heights are probably good enough for what you're coming up with. So, and again, this one, we didn't have quite as much time savings because we had the smaller, tighter radius and the curvature of the back side, but still 35% over ball milling. So that's pretty good. Does anybody have any questions for Alan or I? I mean, we're gonna be out there as well, so we have plenty of time to talk to you, but. Is anybody currently using barrel cutters or have tried? Yeah. And so far, good experience, bad experience?
90% savings.
Yeah. On all sorts of surfaces, or just straight walls, or?
Well, I had questions for you on the mesh thing, because that was one of the complaints my programmers had, was it doesn't do well with the surfaces, you know, if there's multiple surfaces intersecting, and I didn't know that was a possibility, so.
Questions? Anyone? Thank you. Good, thank you very much.
Thank you.
Thank you.